Hi, I'm Fernando Pereira from UFMG, and today we shall see how to use SSA form to enable more efficient and precise static analysis. The first thing that's important to know is that SSA form creates a new branch of analysis that we call sparse. In a sparse analysis, information is associated directly with variable names. It's like if some abstract fact about that variable, like it's constant or it's positive or something like that, could be used as the type of that variable. But for that to be true, one thing is essential. The information associated with the variable must be invariant along all the live range of that variable. In other words, if a variable is constant, it must be constant everywhere where it's used, for instance. Let's show some examples of sparse analysis. We start with that code elimination. We want to eliminate variables that do not contribute to anything useful in the program. How can we do it in SSA form? We can start asking ourselves, what are that variables? Would you like to think about it? So here's a definition of dead variables. Either the variable has no uses, or its uses are only to define other dead variables. That's a declarative definition that uses recursion. And how can we use SSA to simplify this analysis? Basically, we can iterate this algorithm. While there is some variable with no use in the program, remove its definition. Here's an imperative implementation of the algorithm. We count how many times each variable is used. And for each variable that is used 0 times, we remove its definition. By removing some definition, we might remove some uses too. And then we need to update counters. While there are variables with the counter equal to 0, we keep iterating this procedure. Let's talk now about constant propagation. That's a kind of analysis that explains very well the advantages of SSA form. If you remember from the class about lattices, to solve constant propagation, basically we associate each pair formed by a variable and a program point with some element of that lattice of constant propagation. You can see an example on the right side. The important observation here is that the only fact that causes a variable to be a constant or not is an assignment to it. But in SSA form, a variable has only one assignment site. So if that variable is constant at that site, then this information will not change for that variable. Let's see how this works for this example on the right side. You can see the example in SSA form. Let's think about constraints for this program. For each kind of instruction that defines a variable, we can imagine a set of equations to represent that instruction. You can see the equations on the right side of the figure. There are too many symbols here. Let's see what they mean. The double bracket is the abstract state associated with a variable. This abstract state is a point in the constant propagation lattice. Then we have these fractions on the right side of the figure, right here. Basically, the equalities about the line above the lines are premises, like here, the equalities above the lines. Things that must be true so that the thing under the line is also true. For instance, if we have an assignment like v equals v prime, right here, then if the abstract state of v prime is, say, in certain a, which can be a constant or NAC or undef. Whatever, regardless of this abstract state, we will be copying it to the abstract state of V. And we can use similar reasoning for all the other constraints in the program. And when we have a phi function, we apply the meet operator of the constant propagation lattice onto all the arguments of the phi function. Let's see how these equations work in our example. Starting with x0 equals input, we see that the equation for this instruction says that x0 will not be a constant. We associate it with the abstract value NAC in this case, of not a constant. Now, if we have the assignment A0 equals 1 right here, then we associate A0 with the abstract state constant 1 right here. If we have C0 equals A0 plus 10, then we associate C0 with the abstract state constant 11. We do it because that's what the equation of addition tells us to do. You can see the equation of addition right in here. In a phi function, we need to run the meet operator over all the arguments of the phi function. In this case, we have that A0 is 1 and A2 is undefined. So constant 1 meets undefined yields constant 1. And this becomes the abstract state of A1. The abstract state of B0 will be NAC because X0 has this state, NAC. Once we interpret the assignment A2 equals A1 plus 1, then we get that A2 will be associated with the abstract state constant 2. But now we have that A0 is 1 and A2 is 2. The mid of these two abstract states will be NAC, and so this becomes the state of A1 in the definition of the phi function. Remember, when two different constants collide in constant propagation, the abstract state of the resulting definition is NAC. And now we propagate NAC also to B0, which uses A1, and to A2, which also uses A1. And with this, our algorithm terminates. For the abstract state of the variables will no longer change. And that's pretty much how constant propagation is implemented in LLVM, for instance, which uses SA form. You can see the code in the LLVM repository in this figure. You can look at it later if you want, but that's pretty much an algorithm with a working list that evaluates the instructions using that system of constraints that we saw before. Another thing very cool about SSA form is Liveness analysis. In SSA form, we can run Liveness analysis by simply traversing the control flow graph from the uses of a variable until its definition, marking all the edges along the way. For instance, look at this program. Where is I2 alive? I2 is defined at L2. Where is it alive? You can see the places where I2 is alive. They are marked with these little bars. And do you think that I2 is alive at the block with the label 6? The answer is no. A variable is not alive at the phi function where it's used. It's alive only along the edge that leads to that phi function. So, do you think that I2 and I3 could be allocated to the same register? The answer is affirmative, because they are never alive together. Even though they are used as arguments of the same phi function, I2 is alive here, and I3 is alive at this edge, but they are not alive at a common program point. So they could be allocated into the same register. By traversing the control flow graph, from uses towards definitions, we mark the places where a variable is alive, and we never have to iterate. This new way to find live variables work because we are using the key SSA property that the definition of a variable dominates all its uses. So the definition ends up working as a stopping point in our traversal algorithm. And with this last example, we close this class about SSA form. You can see the key references to this class in this figure. In the next class, we shall see some more examples of sparse static analysis. Thank you.